Okay, so today I want to continue a little with the Caldera-Leggett model, and I want to try and get a little more of a feel for what's going on here by going to momentum space. And actually, this is going to be a kind of a vehicle to learn about some integral relations. In particular, I want to exhibit something called the Plummelge relations. And these are two formulae that tell us about how functions that are discontinuous at a point, but otherwise analytic, behave. And this will lead us to a very famous set of relations in the theory of optics called the Kramers-Kronig relations. So let's get started then. So I said what I want to do is go to momentum space with the Caldera-Leggett model. So let's see what I mean by this. So to go to momentum space, I want to make a couple of Fourier transforms. So let's do Fourier transforms on the variables that are the dynamical variables in the Caldera-Leggett model, which is the Q of t that describe the oscillator that we're interested in, and the little q of t, Qi of t, which describes the oscillators that constitute the bath for the system. So taking Fourier transforms, we can write Q of t as the integral from minus infinity to infinity of Q of omega. So normally, I would put a tilde here to indicate that these are Fourier transform variables, but I'm going to denote the variable and its Fourier transform by the same letter, which is slightly abusive notation, but okay. And I'll denote whether we're in t space or omega space just by the functional dependence. So I'm not going to bother putting any tildes in there. E to the I omega t. And my normalization is going to be d omega over 2 pi. Okay. And I will similarly define Qi of t as an integral minus infinity to infinity of Qi of omega e to the, sorry, my convention here was minus I omega t d omega over 2 pi. Okay. So what I do then is substitute these definitions for the q's and the little qi's into the Caldera-Leggett equations of motion. So let me just make a note of what these various things are. So this is the Fourier transformed variables. Those two. And this is our choice of normalization. The 2 pi comes from normalization. So if I substitute this into the equations of motion, I'll find the following. In momentum space, the equations of motion read that minus omega squared, and this comes from taking derivatives, two derivatives in particular, plus omega squared minus, plus delta omega squared. That was that frequency shift variable that we chose. All of this times q of omega minus the sum over I of fi q I of omega. And this was equal to 0. But what I'm going to do here is go for broke and just add an external forcing term. So let's add an external force to this, and we'll add it in momentum space. So we in principle would add an external force, take its Fourier transform, and write this like this. So this is just a external force that acts on the system. And I have another set of n equations that come from the Barth oscillators. And again, two derivatives pulls down a factor of I omega twice plus omega I squared times q I of omega plus f I q of omega equal to 0. The second equation can be solved quite straightforwardly. And again, so the reason we do this is in going to Fourier space, the differential equations become algebraic equations because every time I differentiate, I pull down a factor of omega. So this just gives me an algebraic equation in omega and the variables that I'm interested in. But the second equation in particular allows me to, let's do it this way. The second equation in particular allows me to solve, and this tells me that the qi variables, all n of them, because they're n independent variables, qi of omega can be written as fi over omega I squared minus omega squared times this q of omega, which I can then substitute back into the first equation. So substituting back into here. When I do that, I get that the first equation becomes simply that minus omega squared plus, sorry, this should be a minus here. Omega squared minus delta omega squared times q of omega minus sum over I of fi squared over omega I squared minus omega squared times q of omega, and all of that is equal to this external force F. Okay. So, in the last time we looked at the Caldera-Leggett model in real space, what we did at this point was we looked at this sum here, that we had this sum over the discrete variable, discrete index I, and we replaced the sum by an integral over the spectral function, spectral density of. So let's do the same thing. So now we can take the large n limit and this has the effect of writing the sum over oscillators of Fi squared over omega I squared minus omega squared as an integral normalized by this factor from 0 to infinity of of omega tilde, say, j of omega tilde over omega tilde squared minus omega squared d omega tilde. And similarly, this shift function delta omega squared, which you recall was minus, which you recall was the sum over Fi squared over omega I squared. This becomes 2 over pi, an integral from 0 to infinity of j of omega tilde over omega tilde d omega tilde. Yeah, from 0 to infinity. Okay. So with all of this, stick it into the equation for Q, rearrange it by taking terms to the left-hand side so that I just have something in Q on the left-hand side and just this F external on the right-hand side, divide through by the common factor, and I'll find that I can write then that the solution that I'm after, Q of omega, is just 1 over omega squared minus little omega squared plus something I'm going to call sigma of omega. And all of this multiplies the external forcing function, or its Fourier transform, F external. All right, that's our solution. This quantity here, in fact, this is important enough that we should make mention that this is our solution. So this is our solution in momentum space. And of course, once you have momentum space solution, in principle, you should inverse transform, which we're going to get to just now. But what I want to point out here is that this combination, or rather, this function here, is the combination, it's defined as the combination 2 over pi integral from 0 to infinity of j omega tilde over omega tilde minus omega tilde. Sorry, this is horrible. Do this better. Where sigma, this is not a sum, this is a variable, right? Of omega is the quantity defined to be 2 over pi integral from 0 to infinity with respect to omega tilde of j omega tilde over omega tilde minus omega tilde j omega tilde over omega tilde squared minus omega squared. And this quantity here is called the self-energy, term that derives from the initial application of these methods to high energy physics. This is called the self-energy of the variable Q. Okay. The associated function, this guy here, 1 over omega squared minus omega squared plus sigma of omega, is usually called in the literature G of omega. And this is the response function. Again, an historical term that derives from the original application of these ideas to high energy physics. Now, the response function is well, not high energy, in this case, condensed matter. The response function is, I use the letter G for good reason, because I've told you about this before, but this is nothing but the Green's function associated to the differential operator to this differential operator, which is here written in momentum space. Any questions? Okay, so let's then go back to the Caldera-Leggett model and pick a particular spectral function and show how that spectral function gives rise to a particular integral. And again, I said that this, we've already solved this problem in real space. So you might ask, well, why are you bothering thinking about this in momentum space? What's new to learn here? What's new to learn here is I really want to use this example to motivate a class of integrals that I want to consider. So the statement here is that viscous damping So imagine I put the oscillator Q in a bath of honey, let's say. Viscous damping means that I get to choose J of omega in frequency space as eta times omega. And this gives a self-energy of sigma of omega equal to minus 2 omega squared over, 2 omega squared eta over pi times the integral from 0 to infinity of d omega tilde over omega tilde squared minus omega squared. And I'm going to really be concerned with this integral here. Okay, I'm going to be concerned with this integral here, and I'm going to define this integral to be I, and I is going to be a function of omega because I'm going to integrate out all of the omega tilde dependence. All right. So let's think about this function for a moment. Fortunately for us, these are integrals that we learned to do in first year already. And we did this by looking at the structure of the function and using partial fractions, basically. So to solve the integral I of omega, we notice the following. Notice that I can write 1 over omega tilde squared minus omega squared. So 1 over that. I can write as 1 over 2 omega times 1 over omega tilde minus omega plus, sorry, minus 1 over omega tilde plus omega. And you can check immediately that when you add those two fractions up, you get the fraction on the left-hand side. Which means that I can immediately write then that the integral that we want to solve, I of omega, is just 1 over 2 omega times the logarithm of omega tilde minus omega minus the logarithm of omega tilde plus omega. And I have to evaluate this between omega tilde equals 0 and infinity. Now, at the upper limit, I have to evaluate the log of infinity minus some fixed amount divided by infinity plus some fixed amount, which if I've got infinities and I'm taking away fixed amounts or adding fixed amounts, who cares? So this is like log 1, which is 0. So let's look at the limits. So at the top limit, we get log of infinity minus omega over infinity plus omega, which is more or less log of 1, which is 0. Great. Nothing funky happening up there. At the lower limit, on the other hand, something interesting happens. Here we get the following. We get minus 1 over 2 omega times the log of minus omega minus the log of omega. Well, clearly this is not going to give a real answer, but fortunately, yeah, Keniso.
Oh, so
sorry, I didn't know how long your hand's been up. I didn't see it.
Could you please go back to the previous screen? I wanted to ask something about the integral. So I see your integral is in terms of the omega tilde, and then you're dividing with omega.
Oh, sorry. Yeah.
Oh.
Yeah, it's omega tilde as well. Let's erase that and happy?
Yeah. Thanks.
Good. All right. Very good. Okay, so now how do we address this? Okay, I've got the log of a negative number. So if I take omega to be positive, then one of them is going to give me the the log of minus omega is going to give me a log of a negative number. If I take omega to be negative, then I'm going to get log of omega giving me a log of a negative number. So either way, I'm going to have to deal with a complex number. But fortunately for us, by now, we're pretty familiar with complex numbers. So it shouldn't come as any surprise that I'm going to get a complex number out of it. So let's see how this would work. So this is equal to minus 1 over 2 omega times the log of minus omega over omega. Let me be a little more clear about this. Log of minus omega over omega. Okay, which is minus 1 over 2 omega log of minus 1. But minus 1 I can write as e to the plus or minus I pi. So that's the log of e to the plus or minus I pi. And now I'm taking the log of an exponential. So this is nothing but plus or minus I pi over 2 omega, which in turn implies that the self-energy, sigma of omega, is just minus plus I eta omega. Now, firstly, any questions? Is everybody happy with this? Is anybody happy with this?
It kind of feels like we've done something sneaky.
Yeah. Very good.
Yeah.
So
not too sure what like we're ignoring.
But it kind of makes you feel a little bit dirty.
Very dirty, yeah.
Great. So if you're a mathematician, I'm perfectly happy for you to feel dirty at this point. Sorry, just give me 1 second. There's somebody at my door. I'm just going to pause the recording. Right. So if you're a mathematician, I would totally expect you to feel a little uncomfortable at this point. So let me help you feel. Let me help you feel a little bit more comfortable with what we just did. Right. So to ease your discomfort, I would like you to do the following exercise for me. Okay. So I'm going to ask that you can make this argument more rigorous. So as follows: make this more rigorous as follows. So the way we would do this is in the following 3 steps, and I'd like you to carry this out. So step number 1 is write the log of omega in the following way that involves writing omega in modulus argument form. So if I write omega as mod omega e to the I argument of omega, then that, and I take the logarithm of that, then that tells me that I can write the log as log mod omega, log of the modulus of omega, plus I times the argument of omega, right? In this case, the argument goes between minus pi and pi. Point 2 is give omega some small imaginary part. So add to omega something like plus or minus I epsilon, where epsilon is some small number, and the plus or minus tells you you shift omega up or down off the real axis. I don't really care which won't affect your argument. And then show that with this, sigma of omega plus or minus I epsilon is minus plus I eta omega. Okay, so this is how you would make this argument rigorous. It's basically a shifting omega off the real axis and then showing that the self-energy evaluates to that. Okay, now, do I want to, okay. All right, so I said that really I was using this example as a vehicle for something. And the vehicle here is that we were dealing with integrals of a particular form. So out of this, the lesson that we want to take away is that we would like to focus on a particular class of integrals. So let's call them f of omega. And these integrals are of the form 1 over pi. I mean, these factors of pi don't really, are not really that important, but we'll keep them around because we'd like to touch base with some physical examples. D omega, let's say prime, rho of omega prime over omega prime minus omega. So these integrals occur more frequently than you would think in mathematical physics. And it's worth spending a little bit of time exploring some of their properties. I'll show you an example from optics in a little bit that illustrates this. There's a couple of things we need to point out here, though. One is that the integration variable omega prime runs between A and B. And if omega lies in that interval between A and B, which often it's going to happen that it is the case, then we're going to be in trouble because we've got a pole of the integrand lying on the integration contour, right? So one way to avoid dividing by 0, which is what would happen in that case, is to move that pole in the integrand off the axis by giving it some small imaginary part. So, you know, we do what we just did just now by sending omega to omega plus or minus I epsilon. And when you do that, you can use the following observations about that integral that's called the Plumel formulae to do the integral. Okay. So let's make a note of this. If omega is in the interval from A to B, then what we do is we send omega to omega plus or minus I epsilon and use the following observation. The observation is, there's two observations and they're quite straightforward to write down anyway. The first one says that if I take f of omega plus I epsilon, subtract f of omega minus I epsilon, the value of f evaluated just below the axis, And that's nothing but 2 times I rho of omega, where rho is the numerator of this integrand. Okay. The second observation that I guess Flamel made is if I take the average of the function between those 2 points, so f of omega plus I epsilon plus f of omega minus I epsilon, then this is nothing but 2 over pi times the principal part of the integral from a to b of rho of omega prime over omega prime minus omega d omega prime. Okay, and this is the statement that this is a principal part of the integral, which you will have learned about in your course in complex variables. Okay. And if you haven't, there's a section in my notes that covers it, so feel free to go through that. So these 2 relations together are called the Flamel formulae. They're quite important in the theory of optics, and general scattering theory. And so let's spend a little bit of time unpacking the content of these equations. Okay, the first equation is telling us that the function f of omega, which is usually smooth and analytic, is actually discontinuous on the real interval from a to b. Okay, so this equation here tells us that let's try that again. This statement here tells us that f is discontinuous on the interval from a to b. And in addition, if the numerator of the integrand, this function rho of omega, is itself an analytic function on the line that joins a to b, is itself an analytic function, then the line that joins a to b is actually a branch cut of f of omega. And the points a and b, the endpoints of that interval, are branch point singularities of the integral. And if rho of omega is analytic, in other words, the only singularity that I have comes from the denominator, then f has a branch point, has branch points. As branch point singularities at A and B, and the line from A to B is a branch cut of the integral. Okay, so that's the content of the first equation. We'll get to the content of the second equation just now, but let's see if we can understand this discontinuity in another way, right? I said we're going to assume that the numerator is fine. It's an analytic function. So really the problem comes from the denominator of this expression, right? All the problems that we're encountering comes from the fact that omega lies on the contour of integration, and that will cause that numerator that will cause the integrand to diverge. So let's see if we can think about this in a slightly different way. Okay, so let's notice the following. The problematic piece of the integral that we're concerned with, I'm going to give omega a slight imaginary piece, remember? So this integrand looks like this: omega plus or minus I epsilon. One over. And I'm going to write it as follows. And this is just reorganizing the fraction in a particular way. I'm going to write it as omega prime minus omega squared plus epsilon squared. And in the numerator is going to sit a factor of omega prime minus omega plus or minus omega prime minus omega squared, again, plus a factor of epsilon squared. And in the numerator of this sits an I epsilon. And you can see what I've done here, which is that if I define this quantity to be G, sorry, running out of space here. A small one. If I define the left-hand side to be G, of omega prime and omega, so let's just call it G. If I define this guy to be G, then I've taken this G and I've split it up into two parts. One part doesn't involve any factors of I, and the other one certainly does. So this is the real part of G here, and this is the imaginary part of G. So this is real part of G and imaginary part of G. Okay, and let's plot this and see what happens. So if I plot these two things together, so let's make some axes. And this will be omega prime. And this will be the real part of G and the imaginary part of G. And let's plot what these two things look like. And you can plot what this looks like by yourself, but you will see that it'll come out to be something like this. So this is the imaginary, this is the real part of G, and where it cuts the axis here is precisely omega. And the imaginary part of G is the function that looks like this. And this function is peaked. At omega. Okay, so this is what the real and imaginary parts of this function g of omega, which is the part of the integrand that's the problematic part here. And what we did was we moved omega off the axis of integration by giving it some small imaginary part, either positive or negative. And at the end of the day, we want to take the limit that epsilon goes to 0. So if we take the limit that epsilon goes to 0, we will find the following. So in the epsilon to 0 limit, we will find that 1 over omega prime minus omega plus or minus I epsilon is the principal part of 1 over omega prime minus omega, by definition of what the principal part is, plus or minus I pi times delta of omega prime minus omega, the Dirac delta, right? So basically, the real part, this part that does this oscillation thing, becomes the principal part of 1 over omega prime minus omega. And the imaginary part, the blue curve, you can see as I make epsilon get smaller and smaller and smaller, it squeezes and squeezes and squeezes and preserves its area. So it shoots up to infinity, and that becomes up to a factor of pi, just the Dirac delta function. We can say even more, because if if rho is in fact a real function, moreover, if rho of omega is real, then we can even say the following. If I take this function f of omega minus I epsilon, and I calculate its complex conjugate, and that is the complex conjugate of that whole integral. Okay, so that integral was, where was it? Yeah, 1 over pi, integral from a to b, d omega prime, rho of omega prime divided by omega minus omega prime. Except I'm calculating f of omega minus I epsilon, so sitting in the bottom here should be an omega minus I epsilon. And I want to take the complex conjugate of the whole thing. Means change i's to minus i's, and if I see any possibly complex functions in there, I complex conjugate it. The only possible complex function that could sit in here is this guy here. Remember, the integral is real. The only possible complex valued thing is sitting in here, but I'm assuming that this guy is real, which means that when I take the complex conjugate, I get the function back again. And so this tells me that this complex conjugation is going to give me 1 over pi times the integral from a to b of rho omega prime divided by omega prime minus omega, and remember I change I to minus I, or in this case, minus I to I, and then integrate with respect to omega prime. In other words, the complex conjugate of f of omega minus I epsilon is nothing but f of omega plus I epsilon. Okay. There are two immediate consequences to this. This means the following. The first thing is that the discontinuity across the real axis that we found is purely imaginary. And the second thing is that a half of f of omega plus I epsilon plus f of omega minus I epsilon is nothing but the real part of f of omega plus I epsilon. And now I can take both of these two facts together and combine them. And this tells me that the real part of the integral f of omega is nothing but 1 over pi times the principal part of the integral from a to b of the imaginary part of f of omega, some function omega, divided by omega prime minus omega integrated with respect to omega. And this holds not just for the integral that we started off with. We deduced all of these facts from that integral. This holds for some arbitrary function, actually arbitrary meromorphic function, f of omega. Okay, and this is the beauty of the Flamel formula. And in fact, we can use this Flamel formula to say something physical. And the something physical I want to say is, comes from the theory of optics. Let me stop first and ask if there are any questions. If not, so let's go to the theory of optics, where we're really studying electromagnetic waves, okay, and their interaction with various things, various media. An electromagnetic wave in a vacuum takes a plane wave form, which means that I can write it in some particular mathematical form. And I'm only interested in electric and magnetic fields, but let's just say we talk about the electric fields for the moment. So an electromagnetic wave in vacuum has the plane wave form E of x and t. And in fact, let's just consider one spatial dimension. So I'm not carrying around arrows on my x's. All right, so E of x and t is some amplitude, which I'm going to call E naught, times e to the I k x minus I omega t. Right. So this is a plane wave form, and anytime you see some variable written like this, it's really describing a planar wave propagating in space and time. This quantity omega here is the frequency of that wave. And the quantity k is what we call the wave number. Okay, so this is for a plane wave in vacuum, for an electromagnetic plane wave in vacuum. Okay, this is an important point here. The wave number K, just quickly, can be written as a ratio of omega and the speed of light. Okay, so this is what happens in vacuum. And the question that one would necessarily try to ask here is what happens when the light leaves vacuum and travels in a medium that is not a vacuum? So it travels in some other medium, like glass, for example. Okay. Well, what happens when light travels through a medium is that this relation gets modified, and gets modified in a particular way that encodes the fact that this light is scattering of the things that constitute that medium, right? So all of that stuff is coded in something called the refractive index of the medium. So when this light travels through a medium, this changes to the following relation. E, again, of x and t, is now written as E naught, same amplitude, only now this changes to n of omega kx minus I omega t. And this quantity here is called the refractive index of the medium. And in particular, n of omega is a complex valued quantity that can be written as n sub r of omega plus I over 2 mod k times gamma of omega, where gamma here is what's called an extinction coefficient. And the extinction coefficient is defined in the following way. It's defined via the intensity of the light, and it's defined such that if the light hits the medium with some initial intensity, I naught, say, then there's an exponential fall off in the intensity as the light travels a distance x through the medium. And the gamma is defined through this exponential. So gamma is defined such that the intensity I at a point x in the medium is given by I naught, the intensity that the light hits the medium with, times e to the minus gamma t. So there's this exponential fall off as it travels further into the medium. The real part of this complex number is what we normally call the refractive index of the medium, and specifically nr of omega can be put into the form 1 plus the speed of light c divided by pi times the principal part of the integral from 0 to infinity d omega prime of gamma omega prime divided by omega prime squared minus omega squared. So notice what we've done here. We've got this complex valued function n of omega, and we split it up into its real and imaginary part. Its real part is the refractive index nr. Its imaginary part is this extinction coefficient. And what the Plumel formula in its integral form allows us to do is to write the real part of n of omega in terms of an integral over the imaginary part of n of omega. This relationship between the real and imaginary parts of the complex valued refractive index is what people that work in optics call the Kramers-Kronig relation, or Kramers-Kronig relation in the theory of optics. So if you're studying optics at any point, you will definitely come across this, and it's something that you will come across whenever you study light scattering in different media, and it's a very important relation that allows you to solve that problem, and its mathematical basis is in the Plumel formulae, which itself arises from the study of Green's functions in these kinds of systems. Any questions? Sebastian.
No questions from me.
Okay, sorry, I saw you unmuted yourself and I assumed you had a question. All right. Okay, so that was an example of what I wanted to cover, and that closes off this particular section. What we're going to do next time is look at a very important operator that's kind of the operator equivalent, a generalization, if you want, of the Green's function. It's called the resolvent operator. So I will tell you some really interesting facts about the inverse of differential operators expressed in terms of the eigenvalue problems associated with them on Monday. All right. Have a good weekend, and I will see you guys next week.
Thank you.